The most important thing you're learning now is concepts. I'm not trying to teach you a systematic approach to every kind of problem. I'm trying to teach you some general counting concepts that you can use to a variety of situations, from the very simple to the very complicated. So you'll do best if you don't try to approach a question with the idea that there's a rote formula way of doing it, but rather look at new questions, especially questions that don't look exactly like something you've seen before, and try to think about what concepts you know which can be applied to handle at least some aspects of the questions. The situation we're going to look at now is quite complicated, and it doesn't fit into exactly the mold of any single question we've looked at before, but it offers us a variety of ways to apply some of our concepts. What we're going to be doing is trying to schedule some speakers. We have a meeting that's to be addressed by 5 people whose names are Smith, Jones, Watt, Evans, and Fudd. We're looking at arranging the order of the speakers, and we have to deal with the problem that Fudd insists on speaking before Watt. So the bottom line question is, in how many ways can we order the speakers if Fudd insists on speaking before Watt and we have to accommodate him in that wish? Let's strip the problem down to a simpler problem to think through first. Let's suppose we just had 3 people. Suppose our meeting was to be addressed by people named Watt, Evans, and Fudd. In how many ways can the order of the speakers be arranged if Fudd insists on speaking before Watt? Well, if we just have these 3 people, we can simply enumerate the possibilities. With 3 speakers, there would be 3 factorial or 6 ways of arranging them in a speaking order. That is, if we didn't pay any attention to Fudd's insistence on speaking before Watt. Those 6 possible arrangements are shown here. But of course, in some of those arrangements, we have Watt before Fudd. If we separate out the ones that have Fudd before Watt, the ones where the font is in green are ones that we would eliminate because these have Watt before Fudd. The ones where the font is in red are the speaking arrangements where Fudd is before Watt. We could have Evans first and then Fudd and then Watt. We could have Fudd first and then Evans and Watt, or Fudd, Watt, Evans. These 3 where the font is in red are the 3 speaking arrangements which would honor Fudd's requests of speaking before Watt. So the answer in this case would be 3. So now let's go back to the original question, which involved 5 people. A meeting is to be addressed by people named Smith, Jones, Watt, Evans, and Fudd. In how many ways can the order of the speakers be arranged if Fudd insists on speaking before Watt? Well, let's see. We could certainly put Fudd first. And if Fudd speaks first, then there's no question that Fudd will be speaking before Watt. So any arrangement that has Fudd first would be a legal arrangement that would meet Fudd's request. There would be 4 factorial ways of arranging the other speakers to follow Fudd, since that's just a matter of putting the other 4 people in the other 4 spots. So we could do it 24 ways in which Fudd was speaking first and therefore was speaking ahead of Watt. What if we put Fudd second? Well, if we put Fudd second, and we want Fudd to be speaking before Watt, then that means we can't put Watt first. We can put anybody else first. So if we're going to put Fudd second, that leaves us 3 choices for who goes first. It can't be Watt, and it's not Fudd because Fudd is second. Any of the other 3 can go first, and then after we've picked somebody to go first, the 3 that are remaining, Watt included, can be arranged in 3 factorial ways in the last 3 spots. So just thinking about filling in these 4 spots in order, 3 choices for who goes first, then 3 choices for who goes third, 2 choices for who goes fourth, 1 choice for who goes last. Multiply, you get 18 ways to arrange them where Fudd is speaking second. If Fudd is going to speak third, how do we do the counting? Anybody besides Fudd and White can go first. 3 choices for who goes first. Then after that spot is filled, how many choices for who goes second? Well, it can't be Fudd, it can't be who is first, it can't be Watt, so that leaves only 2 other people remaining to fill this spot. Once that's filled, we'll still have 2 remaining to fill this spot, and then 1 remaining for the last one. 3 times 2 times 2 times 1 is 12 ways to arrange them with Fudd speaking third and maintaining the requirement that Fudd speak before Watt. If Fudd's going to speak fourth, then of course we're going to have to put Watt fifth, and the other 3 can go in any order in the first 3 slots. 3 times 2 times 1 ways of filling these spots. Watt has to go in spot 5. 3 factorial is 6. 6 ways to arrange them with Fudd fourth. Putting Fudd last is not possible if Fudd is to speak before Watt. So we've looked at all the ways to do it if Fudd is going to be before Watt, and we just total up how many we counted. We counted 24 ways of doing it with Fudd first, 18 ways with Fudd speaking second, 12 ways with Fudd speaking third, 6 ways with him fourth. Add them all up, and it's a total of 60 ways to do the arrangements. Now, before we leave this problem, let's take another look and see a little clever way to see why 60 is the right answer. We have 5 speakers. If there were no restrictions on how we ordered the speakers, those 5 speakers could be scheduled in 5 factorial ways. We could put them in any order whatsoever and have 120 possibilities. Now think about the symmetry here. Of the 120 ways, there would be just as many arrangements that put Fudd before Watt as there would be that put Watt before Fudd. So in other words, those 120 ways are going to split, half of them being cases where Fudd is before Watt, and the other half being cases where Watt is before Fudd. That's consistent with what we counted. We counted the 60 ways of putting Fudd before Watt. By symmetry, there would be also 60 additional ways of putting Watt before Fudd, and that's consistent with the fact that we know that there would be 120 ways if you just arrange the 5 speakers in an arbitrary order. Let's take another look at the tennis match, which we've seen before. Kim and Susan playing a tennis match. The winner of the match will be the first person to win 2 sets. We've seen this tree diagram that represents all the possible ways that the tennis match can go. If you're interested in how many sets are played in the match, we can look at the outcomes and see that 4 of the outcomes lie up at this level. 2 of the outcomes lie at the lower level. So we have 2 outcomes that show the match ending in 2 sets, 4 outcomes that show the match ending in 3 sets. 4 of the cases are cases where the match lasts for 3 sets. 2 of the cases are cases where the match ends in 2 sets, a total of 6 different cases. Now in men's tennis, it's common to play matches where the winner has to win 3 sets. How many different possibilities are there for the way the match can go? In a men's tennis, Bob and Tom are the 2 players. In a men's tennis match, how many different outcomes will we have to draw if we drew it into a tree diagram? What I would like for us to do is to try to analyze this without actually drawing the tree. We'll count the number of possibilities where Bob wins the match, and then there would be an equal number of cases where Tom wins the match. One possibility is that Bob could win the match in 3 straight sets. If he wins set number 1, set number 2, and set number 3, then that's one way that the match could go, and the match is over after that third set. So there's one possibility that would show Bob winning the match in 3 sets. How many outcomes would there be in our tree which show Bob winning the match in 4 sets? If he wins the match in 4 sets, that means he must lose one of the sets, right? Because the only reason they would play 4 sets would be, the only way he would win it in 4 sets would be for him to win 3 of 4. Now, the set he loses can't be the last one because he would have won he would have won it previously. So if he's winning 3 out of 4 sets, the set he loses can't be the last one. He's got to be the winner of the last set if it's going to be Bob winning in 4 sets. So the match would have to go something like this. Somebody would have to win the first set, somebody the second, somebody the third, and then Bob would have to win the 4th set. For him to win it in 4 sets, though, how many of these first 3 would he have to win? He'd have to win exactly 2, wouldn't he? Because to win it in 4 sets, he's got to win a total of 3 of the 4, and we know that he wins the last one. So the number of different ways where Bob could win it in 4 sets would be the number of ways where in the 4 sets Bob wins the last one and he wins 2 of the first 3. How many ways can you fill in the chart here showing him winning 2 of the first 3? That's simply a matter of picking from these 3 blanks, picking 2 of the blanks and putting Bob's name there. So that's combinations of 3 things, choosing 2. 3, in other words. For Bob to win in 4 sets, he would have to win 2 of the first 3 sets. Combinations of 3 things, choosing 2 is 3. So we've counted 4 different ways the match could go where Bob wins it in 4 sets. To be specific, he could lose the first set and win the next 3. He could win the first and lose the second and win the next 2. Or he could win the first 2 and lose the third and win the last one. Those are the 3 different ways that Bob can win it in 4 sets. How many ways can Bob win it in 5 sets? Well, if he's going to win it in 5, then it must be the case that he wins the 5th set, and he would have to win how many of the first 4? He would have to win exactly 2 of them, wouldn't he? If he's going to win it in 5 sets, it means he wins 2 of the first 4 and he wins the 5th one. So we would have to have Bob's name in exactly 2 of these 4 spots. 6 ways of doing that. Combinations of 4 things, choosing 2. The number of ways of picking 4 of these spots as places to put Bob's name, putting the other guy's name in the other 2 spots. 6 ways of doing that. So we've counted 6 ways for Bob to win the match in 5 sets. And now we just total. 1 way to win it in 3, 3 ways to win it in 4, 6 ways to win it in 5 gives us a total of 10 different ways that Bob can win the match. He has to win it in either 3, 4, or 5 sets. Those are the only possibilities. 10 ways for Bob to win the match. Turn it around. 10 different ways for the other player to win the match. So that would give us a total of 20 different cases, 20 different possibilities for the way the match could go. Now, if you're willing to draw a big enough tree, you should be able to confirm this. Why don't you get you a big sheet of paper and draw your picture writing rather small. See if you can draw the total tree for a tennis match between Bob and the other guy and show all the 20 outcomes in your tree, all the 20 possibilities for the way the match could go. Examining a World Series in baseball is very similar to this. The World Series in baseball requires that a team wins 4 games. If you drew a tree diagram for a World Series played between the Braves and the Yankees, how many outcomes would your tree show?